construct different molecules, and most of those reactions are done in this kind of flask. Okay. So on the other hand, if you consider living things like living cells, they use only certain kinds of enzymes, which are Mother Nature's own catalysts, in order to sustain life. Okay, so these three scientists were Bertozzi, Melville, and Sharpless. They came up with the idea that how to combine these two paradigms together and take the advantage of it in order to modify living systems. And due to that research, they have been awarded Nobel Prize in Chemistry 2022. So what are the implications of this research? So you can, by doing such kind of chemical modifications, you can achieve some enhanced biological functions from already existing living things. You can develop some new therapy or diagnosis methods down at the cellular level. You can also modulate and monitor chemical functions of living cells and modify biomolecules such as DNAs or proteins in a highly site-selective manner. Okay, but you cannot directly employ the catalysts or reaction conditions from typical synthetic chemistry into living cells. There are strict requirements for that, and the most important requirement is their biocompatibility. That if you want to use catalysts, they should be active enough that they react at ambient conditions around 37 degrees Celsius or so. They should be able to tolerate complex biomedia, because it's not like reaction solution. It's a cytoplasm or some complex environment. And because you cannot heat these biological systems at high temperature in order to promote reactions, so there should be some facility in your system so that you can remotely control or enhance the reaction rates. So we started this research in 2007, developing some nanoreactors for this application. There are already existing platforms to do similar work, which are based on metal complexes, from devices including metals, from metallozymes, which are essentially polymers or biopolymers, including metals, or some even living microorganisms such as bacteria or yeast interfacing with metal nanoparticles or nanozymes. So in our work, we came up with the idea of creating, using nanotechnology and creating some kind of circulated environment within biological system. And the size of that environment or that nanoreactor could be around less than 200 nanometer, so that we can easily include them into living cells. And then with the help of some remotely operable energy source such as NIR light or magnetic field, we can activate reactions in the living cells. How to synthesize such nanoreactors? So we usually start with silica template. We modify its mesoporosity or hollow interior. We can also achieve open mouth cavities and such that. And then we grow gold nano particles or gold metal in nanoscale sizes. Why gold? Because this is biocompatible and it has unique property. When you divide gold into nanoscale, like less than 100 nanometers, so it starts absorbing light very interestingly, and you can control those light absorption properties based on its size and shape. Okay. So this first example I am giving you to convince that how simple silica modification can lead to very interesting structure which can co-accommodate metal nanocrystals, which are very sensitive and sensitive to the inactivation, along with the natural enzymes. So we modified hollow shells with a manganese silicate lid by using a solid state method, which I'm not detailing here. So, and then this manganese silicate lid can be further modified by galvanic chemistry with platinum, palladium, and ruthenium, which are typical metals to conduct chemical reactions. And when you expose this system, we call it jar with a lid. So when you expose this system to some biological environment, which is typically slightly inside cell, the pH is slightly lower, so they can open up. And due to this flat nature or slightly concave nature, these metals actually fall inside the particle. And along with that, we can encapsulate enzyme, which is non-native, which doesn't belong to the cell, such as lipase in this case, and then co-accommodate inside this hollow shell along with metals. By doing so we can actually create a chemobiotic system, in this case palladium nanocrystals and lipase enzyme, and we can conduct some reaction which cannot be done otherwise. So these 100 to 150 nanometer nanoreactors can then be treated with the living cells. Living cells easily take them inside by probably endocytosis, and then by some study which was not very detailed actually. So we could find that these nano devices, they disperse into cytoplasm, they wait there, and so this green color is actually tagged with these nanoreactors. Red color is lysosomes. So they don't, probably they, from before going into lysosomes, they release from the endosome and disperse into cytoplasm. That's our assumption at this point. And then after that, we carry out some chemical reaction to check whether catalytic entities are active inside intracellular environment. But problem with this kind of systems is reactions are a lot slower. Then we came up with the idea that how to combine nano antenna, this kind of plasmonic, corona, and so we came up with a compartmentalized design. So the internal compartment has catalytic nanocrystals modified inside mesoporous silica, and then when we grow some gold nanopetals onto that selectively. So these outside part absorbs light and transfers energy to the interior catalytic chamber, and that's how you can activate reactions by shining light. And similar size, like I explained earlier, you treat with the cells. Cells take up these nanoparticles inside. You shine them with the NIR light, which is biopermeable, and then you can activate these many reactions depending on the catalyst modified in the nanoreactor. The second design in this case is like this bi-layer hollow nanoreactor. We call it nanocatalysomes, just a fancy name, I think. So it's a AU bi-layer material, but there is a specific function of this bi-layer morphology. By creating this gold bi-layer, you create this kind of cavity, and this cavity is very good in harnessing light due to formation of many plasmonic hotspots. So we selectively modify catalytic metals within this bi-layer and activate number of reactions. So this is very flexible method to modify different catalytic entities within single nanoparticle. So one of the problems of gold metal is that it's not catalytically versatile. So you need to interface some catalytic metals with gold nanocrystals. The problem is when you interface non-plasmonic metals on the surface of gold nanocrystal, which is plasmonic, as a thick shell or large particles, they actually quench the plasmonic properties. As you can see, if you modify thick shell onto gold nanorod, its absorption, which is LSPR absorption, comes down to almost very, very low. So we came up with the idea of modifying these gold nanorod surface with highly thin layer, like atomically, like 2-3 atomic layers, which cannot be done with typical chemistry. So we developed a specific method for that, and we characterize this with many methods that very few atoms of catalytic metals are only deposited onto gold nanoparticles, and it helps us to utilize these plasmonic catalytic nanocrystals for carrying out a couple of reactions with very low power light inside cells. The last example which I am going to tell is about multi-modular design. So in this case, you can come up with like York shell structure. So inside this nanoparticle, we have iron oxide core, which is interfaced with a metal of choice, and the outside you have plasmonic shell. Yeah, there also you can modify different metal. So we can actually, by using, because magnetic nanoparticle can be activated by magnetic field, and plasmonic outer part can be activated by light. So we can selectively activate one reaction and switch off another. So we can choose activation source, either light or magnetic field or both, in order to control reaction, even multi-step reactions in a desired way. So in the last 5 years, we have been many journals have been kind enough to accept our work as a cover highlight. And if you are more interested to know our chemistry, we are basically material chemists and trying to apply our systems into biological cells. We have not switched to some animal study or something. For that, we have to collaborate. But our main intention is to show the power of synthetic materials, and when you interface them with biological system and see some new functions. Thank you so much.